This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on eigenvalues and eigenvectors. First, let's look at the geometric notion. So we start with the matrix A, 1, 5, 2, 4, and we start with a vector x, 3, negative 1. Now we can actually graph that vector x over 3, down 1, and we can also multiply this matrix and this vector. And those are the sorts of things we're going to do. Let's first look at the multiplication. A times x, 1, 5, 2, 4 times 3, negative 1. 1 times 3 plus 5 times negative 1. 3 plus negative 5, or negative 2 in the x direction. 2 times 3 is 6. 4 times negative 1 is negative 4. 6 minus 4 is 2 in the y direction. So I could graph both of these. I could graph x and I could graph ax, and we're going to see how they're related to each other. So 3, negative 1 over 3, down 1. Here's x. Negative 2, 2. Here's ax. Assume there's arrowheads on these things. And you'll notice they're pointing in different directions. X and ax are pointing in different directions. Ax is not a multiple of x. The conclusion for this kind of case then is that x is not an eigenvector. The eigenvectors will be pointing in the same direction. There will not be an angle between them. So since they're pointing in different directions, we're going to say that 3, negative 1 is not an eigenvector. Let's take a look at an example at a vector that is an eigenvector. So if I'm looking at 1, 1. So again, the vector 1, 1 is over 1, up 1, just to kind of get a visual for that. But we're going to multiply a times x and see what we get. So we have 1, 5, 2, 4 times 1, 1. 1 times 1 is 1. 5 times 1 is 5. 1 plus 5 is 6. 2 times 1 is 2. 4 times 1 is 4. 2 plus 4 is 6. So the vector ax is 6, 6, and the vector x is 1, 1, and you'll see that they are related to each other. How are they related to each other? Well, here's the vector 1, 1 over 1, up 1 ends at this dot. And there's the vector 6, 6 over 6, up 6 ends at that dot. And you'll see they are pointing in the same direction. This vector ax, 6, 6, is exactly 6 times as much as the first vector, 1, 1. When that happens, our vector x is an eigenvector. So what do we say? Ax is 6x. Multiplying by the matrix is the same as multiplying by a scalar. If that happens, a non-zero vector is an eigenvector. So we would say x is an eigenvector of A corresponding to a certain eigenvalue. What is the eigenvalue? It is the multiple. So the eigenvalue will be 6. X is an eigenvector of A corresponding to the eigenvalue 6. And we usually use the Greek letter lambda for eigenvalues. So if we get a situation where multiplying by the matrix is the same as multiplying by some scalar, then that non-zero vector is an eigenvalue. Is an eigenvector. Let's go ahead and state our definitions. Given a matrix A, if there exists a non-zero vector x and a scalar lambda, we're scaling it up, making it larger, making it smaller, such that ax is lambda x, then x is an eigenvector of A corresponding to the eigenvalue lambda. Again, just make sure you realize x has to be a non-zero vector. Lambda could be negative 1 or negative 2. So when I say pointing in the same direction, we like to see that being positive. That's more natural, but a negative eigenvalue is fine as well. We perceive them pointing in the same direction when in fact they're pointing in opposite directions. So let's take a look at our process here. Another geometric idea. So I've got the vector negative 5, 2. Let's see that. Over 5, up 2. And we're going to see what happens when we multiply a times x. Do we get something pointing in the same direction? Do we get a new vector that is a multiple of the original vector? So we have ax, 1 times negative 5. 5 times 2 is 10. Negative 5 plus 10 is positive 5. 2 times negative 5 is negative 10. 4 times 2 is 8. Negative 10 plus 8 is negative 2. Well, how does this new vector, 5, negative 2, compare to the original vector, negative 5, 2? Are they pointing in the same direction? Well, in fact, they're pointing in opposite directions, but ax is a multiplier of x. So we can see that here is negative 5, 2. which is x, and here is 5, negative 2, which is ax. And you can certainly see that 5, negative 2 is negative 1 times x. So ax is negative 1 times x. We will say that x is an eigenvector of A, corresponding to which eigenvalue? Corresponding to the eigenvalue of negative 1. Now the fact of the matter is any multiple of negative 5, 2 is an eigenvector. So you could argue 5, negative 2 is an eigenvector, or negative 50, 20 is an eigenvector. Relatively easy for us to show that. So to conclude here, we're going to say negative 5, 2 is an eigenvector of A corresponding to the eigenvalue lambda equals negative 1, because ax is negative 1 times x. Now, how do we find eigenvalues and eigenvectors? What I've shown you so far is how to check if a given vector is an eigenvalue, eigenvector pair. But here's our process. We want ax to be lambda x. If that's the case, the vector ax minus the vector lambda x has to equal 0, but that's the 0 vector. So I fix that. Ax minus lambda x is the 0 vector. We put it in bold. We know we mean a 0 vector. Well, lambda times x is a number times a vector, but I want to think of it as a matrix times a vector. So lambda times I times x is still going to be lambda x. But what's nice about this is A is a matrix and lambda I is a matrix, so I can factor out the x and say A minus lambda I times x is 0. We said x had to be a non-zero vector, so this thing has to somehow give me a 0 vector. And the only way that will happen is if the determinant of that first matrix is 0. So if we are solving for eigenvalues, we're going to go ahead and solve for lambda when the determinant of A minus lambda I is 0. A course in linear algebra will give you much more detail on that process. So here we go. We have our vector 1, 5, 2, 4 that we've looked at so far today. I, 2 by 2 is 1, 0, 0, 1. That is our identity matrix. Multiply that by lambda. Lambda 0, 0, lambda is lambda I. But I want A minus lambda I. So that'll be what? 1 minus lambda, 5 minus 0, 2 minus 0, 4 minus lambda. So there is our A minus lambda I. And we want the determinant of that to equal 0. That's what we're heading for. So the determinant of A minus lambda I is 1 minus lambda times 4 minus lambda minus 2 times 5 minus 10. Then let's see, negative lambda times negative lambda is lambda squared. Negative 4 lambda, negative 1 lambda, negative 5 lambda. 1 times 4 is 4, minus 10. So we get lambda squared minus 5 lambda minus 6, which will give me lambda minus 6 times lambda plus 1 when we factor that. Or you could use a quadratic formula if you prefer. Now to find my eigenvalues, I've got to set determinant of A minus lambda I equal to 0. So if that's the case, lambda minus 6 times lambda plus 1 has to be 0. Lambda minus 6 is 0, or lambda plus 1 is 0. So I have found my eigenvalues, as we saw earlier, eigenvalues of 6 and negative 1. So my next task is going to be to find corresponding eigenvectors for these eigenvalues. Now, there are an infinite number of eigenvectors for a given eigenvalue. We are looking for one non-zero eigenvector to represent them. So if I have an eigenvalue of 6 to find the eigenvectors, ax will equal 6x. And then we'll just create this vector x, which I just like to call xy. So a 1, 5, 2, 4 times the vector x, xy, is going to be 6 times xy. Multiplying this, 1x plus 5y will be 6x, and 2x plus 4y will be 6y. Solving this, add negative 6x to both sides. That will give me negative 5x plus 5y is 0. Subtracting 6y from both sides, it'll give me 2x minus 2y is 0. Now here's the key idea. These two equations are the same. They have to be. So I'm just going to plug some number in for x and find out what y would have to be. and usually we use 1s. That keeps it simple. Plug in a 1 for x. If x is 1, 2 minus 2y is 0, 2 is 2y. Y would also have to be 1. So you can usually sort of solve those things mentally. We're looking for a vector that works. If x is 1 and y is 1, that gives me 0. And that will be an eigenvector corresponding to lambda is 6, which again we've seen before. Now, -1, same process. Ax is -1x. A 1524xy is -1 xy. So 1x plus 5y is -1x, 2x plus 4y is -1y. Adding the x to that side, I get 2x plus 5y. Adding the 1y to this side, I get 2x plus 5y. This is even more obvious that they're the same, because they are exactly the same, not just equivalent. So I've got to find a value for x and a value for y that's going to work. 1 is not my best choice here because that's going to go ahead and put me in the world of fractions. So what did I choose to use? Well, let x be 5 and let y be -2. You'll see how the coefficients kind of get me there. 2 times 5 is 10. 5 times -2 is -10. So an x of 5 and a y of -2 will give me an answer for my lambda is -1. So 5, -2 is my eigenvector corresponding to lambda equals -1. All right, let's do one more of these. So there's our A, there's I and lambda I, and we need A minus lambda I. So 2 minus lambda, 3 minus 0, 7 minus 0, -2 minus lambda. I need the determinant of this. So 2 minus lambda times -2 minus lambda minus 3 times 7. Lambda, lambda squared. 2 lambda minus 2 lambda is 0 lambda. 2 times -2 is -4 minus 21. So that gives me lambda squared minus 25, which is a difference of 2 squares, lambda minus 5 times lambda plus 5. So we need to take determinant of A minus lambda I and set that equal to 0 to find our eigenvalues. So lambda minus 5 times lambda plus 5 is 0, gives me lambda is 5 or lambda is -5. And finally, we're going to find the eigenvectors that correspond to both 5 and -5. So we need ax is 5x. Create the vector xy. Ax 2, 3, 7, -2. xy is 5xy. 2x plus 3y is 5x. 7x minus 2y is 5y. Subtracting the 5x from both sides, adding the 5y to both sides, what do we get? -3x plus 3y is 0. 7x minus 7y is 0. Let x be 1. If that's the case, y is also 1. So for that eigenvector, we get 1, 1 for lambda is 5. And again, any multiple of 1, 1 works as an eigenvector, as long as it's a non-zero multiple. And to get the eigenvector corresponding to -5, I need ax is -5x. A 2, 3, 7, -2 times xy is -5 times xy. 2x plus 3y is -5x. 7x minus 2y is -5y. Adding 5x to both sides, here I'm going to get 7x plus 3y is 0. Adding 5y to both sides, I get 7x plus 3y is 0. Again, they are the same. They have to be. So looking at the coefficients, we usually use numbers like those and then change signs to make sure that this works. So what did I choose to do here? I let x be 3, so if x is 3, 7 times 3 is 21. I need this to be -21, so y would have to be -7. But -3, 7 is perfectly acceptable too. Any non-zero multiple of 3, -7 works as an eigenvector of this matrix corresponding to the eigenvalue lambda equals -5. And that will conclude this lesson.